I wanted to tell you one more thing about the hydrogen atom to finish off this part of the discussion, and then I'll move on to something different about quantum mechanics in 3D. For the hydrogen atom, we already figured out that there's a series of possible energies, right? There are these energy levels, E sub n, that I showed you. Okay, and so in general, the expression for this is the negative mass of the electron over 2 h bar squared. And then we have this electron charge squared over 4 pi epsilon naught squared, and then divided by 1 over n squared. So this is the constant of 13.6 electron volts. And so you can see that the energy level is some negative number times a constant divided by n squared. Okay? So when n equals 1, that's a low negative energy, negative 13.6. When n gets large, then we're dividing by n squared, and this is a number that gets close to 0. So it's a higher energy, close to 0. So that I showed you last week. And the remaining point that I wanted to mention briefly is that in experiments, as time goes on, the electron can jump from one level to another. Okay, so if we say the electron jumps from one level to another, and then it absorbs or emits energy. So the change in energy is going to be the delta energy. That's the initial minus the final. So if the electron is going from a higher level to a lower level, it releases energy corresponding to that difference. Right? If it goes from a lower level to a higher level, it has to absorb energy. That's the difference. Right? And so this difference is what's detected in spectroscopy experiments. So in spectroscopy experiments, people observe all possible delta E's. So this is how people first learned about energy levels of hydrogen, is by seeing what are the differences between the energy levels. Okay, so here's a plot that I copied from the textbook. Right? So this is a plot that shows what are the energies, right? Starting at the negative 13.6. It's down here, and going up to E equals 0. Okay. And so you can see that down here, this is the level for n equals 1, and then n equals 2, n equals 3, and then n goes to infinity up there at E equals 0. So you can see that the levels are getting more closely spaced as you approach infinity, right? That there's a big spacing between n equals 1 and n equals 2. And then the spacing gets smaller as you go on up, like based on the 1 over n squared kind of relation. And so if you look at all the ways that the electron can release energy by making a change from a higher level to a lower level, you can see that there are some big jumps when the electron goes from 2 to 1, or 3 to 1, or 4 to 1, right? Anything to 1, right? And then there's a smaller set of jumps here where it goes from something to 2. And then even smaller set of jumps there where it goes from something to 3. And so in each of these cases, the point is that the atom absorbs or emits a photon with the appropriate difference of energies, right? Delta E. That's the E initial minus E final. And then the energy of a photon, as you, may have learned in a modern physics class, right? This is equal to h bar omega for the photon, right? This is like what we studied for a simple harmonic oscillator, because eventually when you get to a more advanced quantum mechanics class that does the theory of photons, it's basically the same thing as a simple harmonic oscillator, right? And so the increment in energy associated with a photon is this h bar omega for the photon, where omega is the angular frequency. And so the omega is the delta energy divided by h bar, or the frequency nu, that is omega over 2 pi. So we could say that's delta E over 2 pi h bar. Or we could go back to the original Planck's constant and say this is delta E over h. Right? The original Planck's constant is 2 pi times h bar. And that frequency goes along with a wavelength. So the wavelength is lambda, which is the speed of light, c, divided by nu. So that would be, 2 pi c over omega, or you could rewrite it in any of these ways. So this is what people see in experiments, right? And if you plug in the numbers, you can see that these changes from something to n equals 1, these are big changes. So they correspond to high energy photons, high frequency, low wavelength photons. And so those are generally in the ultraviolet range. And this series, this set of possible ultraviolet spectral lines, that gets the name of the Lyman series based on who observed it, right? And then the series that are going from something down to n equals 2, that's smaller energy, smaller delta E, so smaller wavelength, smaller frequency, longer wavelength, and the wavelength here is visible. And this is called the Balmer series. which you might have learned about in the chemistry class. And then going up further, you get to infrared wavelengths that go along with these smaller changes, and that's called the Paschen series. Okay, so I just wanted to mention that briefly because that's the main experimental consequence of seeing all these different energy levels, that you can see the delta energies, and that shows up in spectroscopy experiments. Right, and so there are going to be a few questions about that on the homework assignment, which I just assigned. And so that's just to prepare you for that, which brings me back to mentioning, I just assigned a homework for you guys related to the hydrogen atom. So that's a homework number 7, which is posted on the Google Drive, due on April 5th. Okay, so a week from today. After this, I think there'll be probably 2 more in the semester. So probably 9 in total for the semester. Okay, so that is my story about the hydrogen atom. And so there will be some questions about the hydrogen atom on that homework for you to practice with. Any other questions now for the moment? No, perhaps not. Okay. Well, in that case, I would like to go on then to something else, which is related to quantum mechanics in 3 dimensions, but it's maybe a little bit more conceptual as opposed to solving the Schrödinger equation for complicated potential energies. Okay, and so what I want to do now is the subject of angular momentum, because this is a concept that shows up in 3 dimensions, which really doesn't have any analog in 1 dimension. Right? In 1 dimension, there's no such thing as angular momentum, but in 3 dimensions, it really is a big deal. And so let me introduce that for you now. So you remember the idea of angular momentum in classical mechanics. So let me just remind you a little bit. All right, so in classical mechanics, if we have an object moving around a center, right? So here's our origin, and we have some object that's moving like this, momentum P, and there's a radius R out from the origin. The angular momentum about the origin is defined as R cross P. And that is given the letter L, right? And so we already have quantum mechanical versions of the position R and the linear momentum P. Now let's make a quantum mechanical version of the angular momentum L and see what the properties of that might be. Okay, so to do the quantum mechanics for linear momentum, okay, we have already discussed about each component of the linear momentum, right? That there's an x component, which is minus I h bar d by dx, and a y component, that's minus I h bar d by dy, and a z component, which is minus IH bar d by dz. And because these are quantum mechanical operators, they have commutation relations. And in particular, there's a commutation relation between the position and the momentum. That if we look at the I component of position and the J component of momentum, the commutator between those things is IH bar delta IJ, right? So if you have the X component of position and the X component of momentum, you have a non-zero commutator. But if you have the X component of position and the Y component of momentum, the commutator is zero. As those operators commute, it doesn't matter which one goes first. Okay, so now let's see about angular momentum. All right, so classically for angular momentum, as I said, there's this cross product, right? That the angular momentum is R cross P. And so this is a vector equation, cross product equation. So you know that it's really three equations in one, right? This means that L sub X is Y PZ minus Z PY. And Ly is Z PX minus X PZ. And Lz is X PY minus Y PX. Okay. And you can remember the pattern here because there's like a cycle of X, Y, Z. And you can make cyclic permutations going around there. So when you go from one equation to the next, the X's change to Y's, and the Y's change to Z's, and the Z's change to X's. And that keeps going forwards. Okay, so now, if we want to do the quantum mechanical analog of that, we would say for quantum mechanical angular momentum, we can make everything be an operator. All right, so we would say the angular momentum in the X operator should be the Y operator acting on the PZ operator minus the Z operator on the PY operator. And likewise for Y, and we'll keep doing the cyclic permutations. So ZPX minus XPZ. And the Z component of the angular momentum is XPY minus YPX. Okay, so this makes a nice definition of these three components of angular momentum as quantum mechanical operators. Now, you might be wondering, how do we know which of these things should go first, Y or the PZ, right? Because after all, in classical mechanics, over here, well, these things are just numbers. And so we could have written PXY, PZY instead of YPZ, right? And so how do we know which should go first when we make this generalization to quantum mechanics? Luckily, it doesn't matter, right? Luckily, it doesn't matter because y and pz commute with each other, right? That's the commutator back here, right? If we put in I is y and j is z, but the commutator is 0. So they commute with each other. So luckily, we don't have to decide here whether we write ypz or pzy. It's the same thing. Okay? And that's true for all 6 terms here. All right. That either way, in any of these 6 terms, it doesn't matter which one goes first. Okay, so here are definitions of the operators. Okay? So now that we have these definitions, we have some quantum mechanical operators to work with. And what people often do with quantum mechanical operators is to calculate commutators, right? So we're going to work out the commutators and see what about Lx and Ly? Do those things commute with each other, or is there any commutator we need to think about? So let's figure it out using the stuff that we already know. Okay, so if we want the commutator of Lx with Ly, let's see, that is y pz minus z py commutator with z px minus x p z. And all these things are operators. I may sometimes forget to put the little hats over them, but they are all operators. Okay, so now let's expand all of this. Okay, so if we want to work out these commutators, we could say the commutator of this thing with the difference, that's the commutator of this thing with that, minus the commutator of this thing with that, right? So we can do that expansion, and then we can do the expansion on the first side also. Okay, so we get 4 terms. Okay, so y pz commutator with z px minus y pz commutator with x pz minus z py commutator with z px, and then plus z py commutator with x pz. Okay, now what are these commutators, right? Are they going to be 0 or not? Well, let's take a look at one of them. Okay, so let's look at this guy, for example. Okay, so if we look at this guy, this is ZPY, ZPX minus ZPX, ZPY. Okay. But everything here commutes with everything else. There's no commutation problem for Z with PX or Z with PY or PX with PY. So, this is equal to Z squared PX PY. This is equal to Z squared PX PY, right? It's just, this is equal to 0. Right? There's no commutator there. The same is true for the second term. Here also, x and y commute with each other, and they each commute with pz. So there's no commutator there either. But with the other two terms, it's a little bit trickier than that, because with the other two terms, they include stuff that doesn't commute. They include a PZ and a Z, right? And the same here, it includes a Z and a PZ. Okay, so there we have to do a little bit more work. All right, let's do it. So we can say this is, well, in the first term, let's factor out the stuff that commutes with everything, right? So in the first term, we can factor out a Y because it commutes with everything. And we can factor out a PX because it commutes with everything. What's left is the commutator of PZ, whoops, excuse me, PZ with Z. Okay, what about the next term, the last term? Okay. Now we can factor out a PY because it commutes with everything. And we can factor out an X because it commutes with everything. But we still have the commutator of Z with PZ. Okay, are we good so far? Once again, I forgot to open the chat in advance. So if you're chatting with text, you better just speak up instead. Okay, so you got all this. All right, now we know what these commutators are. Okay, the commutator of Z with PZ is IH bar. The commutator of PZ with Z, that's the negative. So that's negative IH bar. Okay, so then what we are left with is, if we factor out the IH bar, because those are just numbers, and so now writing the second term first, X PY minus Y PX. And now we look at that difference and say, oh, I recognize that guy. That's the Z component of angular momentum. Okay? So this is IH bar L sub Z. So this then is a commutator which tells us about the operator properties of the angular momentum in quantum mechanics. All right, so to write that over here, the commutator of Lx with Ly is IH bar Lz, and the same things apply if you just permute all the indices forwards. Okay, so we get the commutator of Ly with Lz is IH bar Lx. And the commutator of Lz with Lx is IH bar Ly. Okay, so that shows us how to do commutation relations for angular momentum. And it, right, so I proved the first thing, the second and third you can prove for practice with the same method, or you can just reason it works by permuting all the indices forwards. Okay, so this tells us the commutation relation if you look with Lx with Ly. What if you want to say Lx with Lz, well, that's just the opposite of what's written right down here. And so that is negative I h bar Ly. Okay. And the same thing works, if you permute all those indices as well, right? So you would get Ly with Lx is minus I h bar Lz, and Lz with Ly is minus I h bar Lx. And for Lx with Lx, well, any operator commutes with itself. And so that's just 0. Right? This is Lx squared minus Lx squared. So that's 0. Right? And the same for Ly with Ly and Lz with Lz. Okay, so these commutators, these 3, and of course these 3, tell us something important about angular momentum. And in particular, they tell us that Lx, Ly, and Lz are incompatible operators. Right? So you remember, we've talked about incompatible operators before, right? The idea is that these operators do not have the same eigenvectors. That is, the eigenvectors of Lx are not eigenvectors of Ly or eigenvectors of Lz, right? Each of these operators has to have its own set of eigenvectors, which are different from the other ones. Right? And likewise, it tells us that there is a generalized uncertainty principle. You remember the generalized uncertainty principle says that there's a product of uncertainties between any 2 operators, which is related to the expectation of the commutator between them. Right? And so that means that the uncertainty in Lx times the uncertainty in Ly is greater than or equal to 1/2 of the absolute value of the expectation value of the Lx Ly commutator. Okay? And this commutator we just worked out, that's I h bar Lz. And so this uncertainty, this product of uncertainties, Lx times sigma Ly is greater than or equal to h bar over 2 times the expectation value of Lz, absolute value. So we cannot find any state with specific values of Lx and Ly and Lz simultaneously. So that's frustrating for people who like certainty, but that's the way it goes in quantum mechanics. Now, you might ask, what about the magnitude of angular momentum? So let's think about L squared. Okay, so with any vector, there's a square of the vector, which is a scalar. So that would be Lx squared plus Ly squared plus Lz squared. Okay, so suppose we want to figure out properties of this operator, right? Here's another quantum mechanical operator. Let's figure out properties of this operator and see, is it compatible with any of the other ones? Okay, so let's do the commutator of L squared with Lx, for example. Okay, so this is the commutator of Lx squared plus Ly squared plus Lz squared with Lx. So we can break that up. Okay, so that is commutator of Lx squared with Lx plus the commutator of Ly squared with Lx plus the commutator of Lz squared with Lx. Okay, let's figure this thing out. All right, well, the first term is the easiest, right? So this term, right, this is Lx squared Lx minus Lx squared. So that's Lx cubed minus Lx cubed. So that's 0. No problem with that. All right. What about the other two terms? Okay, so this combination, this is Ly squared Lx minus, I can leave a little bit of space there, Lx Ly squared. All right. And then the next commutator is plus Lz squared Lx minus Lx Lz squared. Okay, and then if I want to work this out, a nice trick is to add and subtract the same thing. Okay, so here I could say minus Ly Lx Ly plus Ly Lx Ly. And likewise, in the middle of the second line, I can say minus Lz Lx Lz plus Lz Lx Lz. That's true. Okay. So now let's simplify this thing. Okay. So in the first pair of terms right here, oops, I didn't need to do that. In the first pair of terms right there, what I meant to do is to say, this is, I'll factor out an Ly in the front. Then the commutator of Ly with Lx. Okay. Then for the second pair of terms, right here, I'll factor out an Ly on the back side, on the right side. And then here is the commutator of Ly with Lx. Okay, and then what? I'll do the same kind of trick on the second line. So this is Ly Z, and then the commutator LZ with LX plus the commutator of LZ with LX times LZ. Okay. Now we can simplify all of this because we already know those commutators. Okay, so this is all, oops, where am I going to write it? Equal to Ly, let's see, the commutator of Ly with Lx, that is negative I h bar Lz. Okay. And then what? Plus negative I h bar Lz times Ly. Okay, and then on the second line, plus Lz, and then I h bar Ly plus I h bar Ly times Lz. Okay, so now look at what we have here. This then, the last term right here, oops, the last term right here, I h bar Ly Lz. Okay, how about the first term here? Negative I h bar Ly Lz. Those things cancel each other. Okay, and what about the third term here? Okay, it's I h bar Lz Ly. And the second term, negative I h bar Lz Ly. So those terms cancel each other. So all of this equals 0. So that argument shows us, right, L squared commutator with Lx equals 0. These things commute. And likewise, the commutator of L squared with Ly equals 0. And the commutator of L squared with Lz equals 0. So these are compatible operators. So we could say L squared is compatible with Lx and Ly and Lz. So that means we can simultaneously diagonalize L squared, and one of the Lx, Ly, Lz. Okay. The word diagonalize, I can't remember if I've used that in this semester. We can simultaneously find eigenvectors. Okay, so we can find a set of eigenvectors that work for both L squared and one of the components of L, but not for all of the components of L, right? We proved that's impossible, okay? So we can diagonalize L squared and pick one of the three components, but not the other two. Okay, so the choice that I will make the choice that everybody makes is LZ, okay? Let's choose LZ, okay? So we want eigenvectors of L squared and LZ. Okay, so if we want that, okay, that means we want to find some states so that L squared acting on the state F is some eigenvalue times that state. And LZ acting on the state is some other eigenvalue times that state. So you can see the F is the eigenvector or eigenstate. And it's the same F there and there and there and there, right? All the same F, right? And the lambdas and mu's, these are eigenvalues. And it's not the same eigenvalue. Right? We have two different operators, which even have different units from each other, right? And so the units of lambda and mu are different. So these are definitely not the same eigenvalue, but it works with the same eigenvector, the F. Okay, so that is our mathematical job, okay? So we want to find what are the eigenvectors and what are the lambda eigenvalues and what are the mu eigenvalues, okay? So that's a mathematical job for us to work on, okay? So I'm going to show you a nice trick for calculating this, and then it'll take a little while. It may take the rest of today or even tomorrow, I'm not sure. But eventually we're going to get to an answer, and then we can work with it and do stuff with it. Okay, so the trick for doing this is a ladder operator technique. Okay. And so this is actually a little bit similar to what we did with the harmonic oscillator. So one of the reasons why I showed you the ladder operators for the harmonic oscillator is that we're going to use the technique again here now. Okay? It's not exactly the same, but it's related. Okay. So you remember with the harmonic oscillator, we defined the operators A plus and A minus, which could take any state and shift you to a higher state or to a lower state in the energy spectrum. Okay. Similar trick here. Okay, so we're going to define a pair of operators. L plus and minus, which are equal to Lx plus or minus I Ly. Okay, so as usual, this is two equations in one, right? This is an equation that L plus is Lx plus I Ly, and L minus is Lx minus I Ly. Okay, so I want to show you what these operators do and how these things can be regarded as ladder operators. So once again, we can figure this out using commutators. Okay, so it turns out to be a useful technique. Okay, so first, let's see about the commutators with L squared. So we have the commutator of L squared with L plus or minus. So that's the commutator of L squared with Lx plus or minus I Ly. So that's the commutator, L squared with Lx plus or minus I times the commutator of L squared with Ly. But we know those things, right? The commutator of L squared with Lx is 0. Commutator of L squared with Ly is 0. So this whole commutator is 0. Okay? L plus and minus commute with L squared. Okay, now what about the commutator with Lz? So Lz commutator with L plus or minus. Right. So that is Lz commutator with Lx plus or minus I Ly. So that is Lz commutator with X plus or minus I times Lz commutator with Ly. Now this thing is I H bar Ly. This thing is negative I H bar Lx. Okay, so what does this all make? Okay, this all makes I H bar Ly plus or minus times I squared. Well, I squared is -1, right? So it's minus or plus H bar Lx. Okay, so then I can did I get that right? Minus negative I bar. Wait a minute, I made a mistake here somewhere. Plus or minus.
I think it should be plus or minus. Plus minus.
Thank you. Is that swastik? Thank you. I appreciate that. Yeah, you saved me here. Okay, let's get this right. Because here, this is, I have an I times negative I. That's 1, and there's still a plus or minus. Aha, plus or minus H bar Lx. Yes, that's what I wanted. Thank you. So now I can factor out the H bar. I can factor out a plus or minus. That would be cool. All right. And then there is Lx, and then plus or minus I Ly. Okay. So you can see if I have the top signs, it's plus times plus I Ly, and that agrees with what's over here. And the minus times minus makes a plus, and that agrees with what's over there. Okay, much relieved. Okay, so this is equal to plus or minus H bar times L plus or minus itself. Okay, Now, let's do the ladder operator kind of argument. Okay, so let's suppose that some function f is an eigenstate of L squared and LZ. Okay, so that L squared acting on F is lambda F, and LZ acting on F is mu F. Okay. Now, consider the state L plus or minus acting on F. So this is, supposing we know one eigenstate, let's consider what happens if L plus or minus acts on that eigenstate. Is it still an eigenstate? Well, find out. Okay, so what is L squared acting on L plus or minus F? Okay, so that's L squared, L plus or minus F. But we just proved that L squared and L plus or minus commute with each other. So this is L plus or minus acting on L squared F. And we know what L squared F is from the equation right up here. Okay? That's equal to lambda times F. So this is L plus or minus acting on lambda times F. So this is lambda times L plus or minus F. So, therefore, L plus or minus times acting on F is an eigenstate of L squared. I should say it's also an eigenstate, right? We had one eigenstate of L squared. Now we have another eigenstate of L squared. And with the same eigenvalue lambda. Okay, so if we have one eigenstate of L squared, this will generate another eigenstate of L squared with the same eigenvalue. Okay, what about LZ? Okay. So what happens if LZ acts on L plus or minus F? Okay, so this is right, LZ, L plus or minus F. Okay, I want now to relate that to what happens if I switch the order of those two operators. Okay? But we know it matters which order they are in. We know exactly how much it matters, right? This is equal to L plus or minus LZ, and then minus L plus or minus LZ plus LZL plus or minus. All of this acting on F. Right? So all of this stuff, this is the commutator LZ with L plus or minus. And we know what this commutator is, right? This commutator is equal to plus or minus H bar L plus or minus. Right, because that's what we found back here. Okay, so now let's keep going. Okay, so this is all equal to L plus or minus acting on LZ, acting on F, and then plus or minus H bar L plus or minus acting on F. And we know what is LZ acting on F because that was one of our assumptions up here. LZ acting on F is mu F. So this is L plus or minus acting on mu F plus or minus H bar plus or minus acting on F. So that is mu times L plus or minus acting on F plus or minus H bar L plus or minus acting on F. Each of these terms is some number times L plus or minus acting on F. So this is the sum or difference of those numbers. Mu plus or minus H bar times L plus or minus acting on F. Okay, so from this, we conclude, therefore, L plus or minus acting on F is an eigenstate of LZ with eigenvalue mu plus or minus H bar. Okay, so we started with one state F that's an eigenstate of both operators, L squared and LZ. We got a new state that's an eigenstate of both operators, L squared and LZ. The L squared eigenvalue stays the same. The LZ operator changes. The LZ operator either gets incremented up by H bar or down by H bar, depending on whether you have L plus or L minus. Okay, so we could say L plus raises the LZ eigenvalue by H bar. And L minus lowers the LZ eigenvalue by H bar. And then they L plus and L minus keep the L squared eigenvalue the same. Okay, so that means then that for each L squared eigenvalue, whoops, that's a singular, eigenvalue, there's a ladder of LZ eigenvalues. So that means we start with this state, our initial state F, that has an LZ eigenvalue of mu. And we can raise it to mu plus h bar, mu plus 2h bar, etc. Or we can lower it to mu minus h bar, mu minus 2h bar, etc. All right, and all of this goes with the L squared eigenvalue of lambda, right? The whole ladder goes with the L squared eigenvalue lambda. All right, so now you can recognize the analogy with the simple harmonic oscillator, right? With the simple harmonic oscillator, we also could raise or lower the eigenvalues, in that case for energy, by a certain increment h bar omega. But there's a difference, okay? When we were dealing with the simple harmonic oscillator and the energy eigenvalues, right? I argued for you then that the ladder was a stairway to heaven, right? In the sense that it has a bottom, but it doesn't have a top, right? For the simple harmonic oscillator, there's a ground state, there's a lowest possible energy state, but there's no highest state. It just keeps going up and up and up and up, okay? But in this case, it's different. In this case, there is both a top and a bottom. Okay, so let me write that down and I'll try to prove it. Okay, so the ladder must have a top and a bottom. Okay, so to prove it, say, why? Well, we know that the the expectation value of L squared, well, that's the expectation value of Lx squared plus Ly squared plus Lz squared. And, Lx squared and Ly squared, those things are positive or zero, but for sure they're not negative. Right? So this all has to be greater than or equal to the expectation value of Lz squared. Okay, now, if we are in a state that is an eigenstate of L squared, okay, then this expectation value, that's lambda. Okay. Likewise, if we are in a state that's an eigenstate of Lz, then the Lz squared expectation value, that's the Lz eigenvalue squared. Okay, so greater than or equal to. Okay, so the Lz eigenvalue squared has to be less than or equal to lambda. So the Lz eigenvalue has to be something between square root of lambda and negative square root of lambda, right? That's limits at both ends, okay? And so there must be a top and a bottom, right? The top cannot be higher than the square root of lambda. It might be lower than the square root of lambda, but it can't be higher than the square root of lambda. Okay. So we can say, suppose there's a top and a bottom, right? And so suppose the top eigenvalue of LZ is mu top, okay? And likewise, suppose the bottom eigenvalue is mu bottom. Okay, now this gives us some information about what are the corresponding states, okay? Well, actually, I'm running out of time. Okay, let me set this up and then I'll solve it tomorrow. Okay, I meant to say, suppose the top eigenvalue of LZ is mu top, and the corresponding eigenstate is F top. Okay, and likewise on the bottom. Okay, so suppose the bottom eigenvalue of LZ is mu bottom, and dot, 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 corresponding eigenstate is F bottom. Okay, so what do we know about the top? Okay, one thing we know about the top is LZ acting on F top has to be mu top times F top. Okay, what else do we know about it? We know that L squared acting on F top is lambda F top, because all of these states have the same L squared eigenvalue lambda over here, right? And what else do we know about it, right? Well, we know the top state is on the top, right? And what happens if you try to raise it, right? So if you hit the top state with L plus, well, the only possible answer is that this must be zero, right? That's the same argument we had at the bottom of the harmonic oscillator ladder, right? That if you try to go beyond the limit of the ladder, you have to annihilate the state, that you just get zero. That's the only way for all of our rules to be consistent. Okay, so here we have three relations for F top, right? That we know the eigenvalues and we know that what happens with L plus. And likewise on the bottom, okay, the same kind of relations apply. Amazingly enough, these equations are going to let us solve for what are the eigenvalues. And we're actually getting close to there, but I ran out of time. So I will finish this story tomorrow. Okay, so I'll catch up with you guys tomorrow, same time. and finish, and we'll use this information to figure out stuff about lambda and mu. Okay, I'll stop here and answer any questions if there are any, and otherwise see you tomorrow.